let's get started. Hey, so PS8, I guess it is out and due end of this week. PS9 will come out the end of the week and be due in 2 weeks, since spring break is mercifully upon us.
Yeah.
Yes?
Would you say that it's helpful to work on it like during spring break, or is it still manageable to do?
Oh, it's not intended to be a 2-week assignment, so it's you can just follow your usual habits.
Assuming they work.
So they work, your habits are working for you. Any other questions, problems? Okay, so one of the problems, the CAS problem this week, you have to come up with a greedy. It's an algorithm. It's a problem you can solve with a greedy algorithm. So you got to come up with a way of making a greedy choice. So the challenge when you're doing a greedy algorithm is to somehow convince yourself that your method of selecting, of making a greedy choice is correct. So how do you do that? Yeah.
Could you re-go over exactly what defines a greedy algorithm?
Okay. So we ask what defines a greedy algorithm. A greedy algorithm. So you use greedy algorithms to solve optimization problems. So the optimization problem is one where you've got to make a series of choices to solve a problem, and the set of choices that you make has to be the best in some sense. The smallest, the longest, the largest, and so on. And we'll be looking at a variety of ways of approaching optimization problems. The simplest way is if you can find a greedy algorithm. So what a greedy algorithm is, it's an optimization problem where you can efficiently recognize one choice that's guaranteed to be safe to make, that's definitely in the optimal set, such that you can make that choice efficiently, reduce the problem, because now you've made one choice, so that simplifies the problem somewhat, and repeat. So you just pick, and you're done. As opposed to, say, a backtracking solution would be pick, oh, I'm stuck, back up, try another way, back up, try another way, end up looking at most of the possibilities. That's one extreme, having to look at all the possibilities. Problem with that is there can be an exponential number. At the other extreme, it's a greedy algorithm, which just quickly makes the picks all in a row. So the key is being able to make the choice. So, how do you make the choice? Not how do you make the choice, but when you have devised a way to make the choice, how do you convince yourself that it's a good way to make the choice? Yeah?
Can't you just look at the problem itself and find the best solution and see if your greedy algorithm gets to the same solution?
Okay, so he suggested, look at a problem and see if your algorithm gets to the same solution. Okay, that would show that it works for that problem, but how do you know it works for all problems? Yeah.
Try and come up with a counterexample.
Okay, I'm glad you said that, because there are one approach is to try to prove to yourself. It's possible to prove, and we'll look at a way of proving today that a greedy choice is correct. But my money is on finding counterexamples. So when I'm doing something, I've got a choice between coming up with a counterexample to show that it's wrong and trying to prove that it's correct on the other hand. I always first go for the counterexample approach. Take your greedy choice and then just start thinking of simple counterexamples that'll break it. And if it withstands counterexamples for a while, then try it out. It can be difficult to prove that it's correct. It's a lot easier to throw counterexamples at it. So that's what I suggest you do on this problem.
Edge cases.
Yeah, think of edge cases that break it. Okay?
Big Ns. Okay,
so we looked at the minimum spanning tree problem is an optimization problem, and we looked at 2 algorithms. We're going to look at it in more depth today. Okay, just to remember, we've got an undirected graph that's weighted. We're going to assume it's connected, so no islands. And we want to find the spanning tree of such a graph is going to be v minus 1 edges. If you have more than v minus 1, you have a cycle. So v minus 1 edges that connects all the vertices together into a tree. And we're looking for the smallest such thing, the lightest such tree. So it's an optimization problem in that you just got to pick v-1 edges and do it in such a way that you get the lightest tree. So for this one, we've looked at this example before. There is one minimum spanning tree. There are others. 13 is the best you can do. Okay? Kruskal's algorithm is one approach, and there the greedy choice is to repeatedly choose the lightest edge and create a cycle. So our first choice would be that edge 1, and then one of the edge 2s, and then the other edge 2. So far, none of those form a cycle. Then the edge of weight 3 would form a cycle, so we can do that. We've got our choice of edges of weight 4. I'll take that one. These two edges of weight 4, we create a cycle, so we're just left with that choice right there. And that's all. That puts it together to a tree. So that's just a greedy choice. If you have an efficient way of finding the lightest edge that does not create a cycle, which is the whole trick, then you've got an efficient way to solve the problem. No backtracking necessary. Just forge straight through to a solution. Yeah?
I think I might have talked in the last lecture, but can you have more than one minimum spanning tree for a given graph?
Sure. Like for this one right here, we could take out this edge and put in either of these, and you still have a minimum spanning tree. So you can have ties. They're all going to have weight 13, I think it was. All right, this is a different approach, Prim's algorithm. And it works, it's very reminiscent of Dijkstra's algorithm. It's virtually identical. You start somewhere, doesn't matter where you start. And then you grow the tree in a similar way that you grow the tree in Dijkstra's algorithm. Basically, you find the lightest edge out of a yellow vertex. So the yellow vertex are ones that have been incorporated into the spanning tree. So initially, A is the only one. We take the lightest edge out of the A clump, out of the yellow clump, right there. And now C is part of the clump. Now you find the lightest edge out of the AC combination. And it's going to be that edge 2. Now, how is this different from Dijkstra's algorithm? In Dijkstra's algorithm, you have a clump of yellow vertices, if you will, that have been incorporated to the tree. And at each step, you pick an edge that goes from a yellow vertex to a white vertex, just like here. So what's the difference in the way the choice is made here versus the way it's made in Dijkstra's algorithm? Yeah?
It could be any edge in your set of yellow edges instead of just the edge that
Say it again.
It could be any lightest edge out of your set of edges in this instead of just the vertex you're currently at.
Well, in Dijkstra's also, it could be, if you're doing Dijkstra's algorithm, it would consider all these 5 edges that leave the yellow complex. But you don't necessarily pick the lightest edge that leaves the complex. What do you pick? Yeah?
Dijkstra does minimum path. This one does minimum just edge weight.
Okay, so we said Dijkstra does minimum path. With Dijkstra's algorithm, we're going to pick the edge that leads to a white vertex that yields the shortest path back to the root. So, like this one would have a value of 3. Taking this edge would give us a total path length of 3. Picking this one would give a total path length of 4. So in this case, Dijkstra's algorithm would pick the same edge. Let's see if we can find a place where it diverges. Okay? Now we get the lightest edge out of a yellow vertex to a white vertex. And it's going to be one of those 4s. Okay? So we could pick this one.
Read slower. BC.
Which one?
BC. Oh, that's a 4.
Okay? So Dijkstra's would not pick this edge. Dijkstra's would not pick this edge. Because both these edges leave a path of 5 back to the root. So Dijkstra's would pick this one. And in my animation I do as well. Then there and there. So in this case I believe the minimum spanning tree is identical to the shortest path tree, but it's not necessary. It's often different. Okay, so we're just growing the tree. So those are our 2 algorithms. So we're about to look in them and see why they work, why they're correct. But are there any questions about how they work before we worry about why they work? Yeah?
You said it was doing something different. I must have missed what it's doing different.
What it's doing different from Dijkstra's algorithm? Yeah, we'll go back to this situation. Okay. Dijkstra stores on the part. So Dijkstra's algorithm would have B and F stored on the priority queue. The weight of F on the priority queue would be 5, because that's the distance back to the root. And the weight stored for B would be 4, because that's the distance back to the root. So Dijkstra always picks the white vertex that's closest to the root. So it would always pick this vertex. Okay? Prim's algorithm picks just the edge, the vertex that's connected via the lightest edge. So the weight for, it also uses a priority queue, but the weight for B would be 4. The weight for, this weight would be 4. So it wouldn't, it could take either of these or that. Yeah?
So it's just not doing the update operation, like it's not doing that comparison.
Yeah, I guess that's, yeah, there's not an update operation. The weight associated with the vertex is just the weight of the edge that leads into it. Yeah?
So prims might pick B to D or B to C, which are the
Right.
same for it as A to B, but
Yeah.
Dijkstra's would always pick A to B.
Yeah, Dijkstra would always pick A to B. This would be terrible. Dijkstra would pick this. This is like, in Dijkstra's algorithm point of view, this is the weight of 7.
Mhm. So that's one way they're different.
Yeah, I mean, that's the way they're different.
Yeah.
Is how they, their views of priority queue, they got the same loops, they got the visited array, they got all that, but they determine the weight of a vertex differently, yeah.
Are shortest path trees also minimum spanning trees?
No, shortest path trees don't have to be minimum spanning trees. Okay, let's see if we can concoct one. Since, okay, so let's see if we can create a 3 vertex right. Okay. Anyone suggest a tree where first the minimum spanning tree is different from the shortest path tree?
A to B is 2, B to C is 2, A to C is 3.
So this was, A to C was 2.
3.
3,
And
and this
2.
is 2. Okay, so let's say we're talking about a tree rooted at A.
Yep.
Okay, so let's do this. What's the shortest path tree? What would Dijkstra's algorithm find, or Bellman Ford?
A goes to B and A goes to C.
Okay, clearly the shortest path from A to B is right here. And the shortest path from A to C is right here. So that's the shortest paths tree. I mean the minimum spanning tree. No, that's the shortest path. That's the shortest path tree. Now, what's the minimum spanning tree rooted at the same place?
It's B to C.
Right? You would do, we still got this, 2, 3, 2. It would be this and this. Right? That hooks everything together with a total cost of 4. This one, if you evaluate that as a minimum spanning tree, it has a weight of 5. So that's clearly not the best. Yeah.
What's valuable about a minimum spanning tree, and why are they used, why do we care?
Okay. Okay. Who has an idea? Why would a minimum spanning tree be interesting? Yeah?
Networking applications?
Okay, networking applications, you want to hook together a bunch of routers, let's say, with the least delay or distance or whatever. Yeah?
If you had to go to B and then go somewhere else from there, like in this example,
Mm-hmm.
you had to stop at B and then go from there on your way from B.
Okay, that's specific to that graph. Yeah?
We're talking about traveling salesman and like any mail route or anything like that, you're gonna want to hit every single house in an area. You don't care what the shortest distance between where you start and the houses, you want to hit every house.
Okay, so he's comparing it to this traveling salesman problem, which is a little different. There you want to find a path that visits every vertex once and doesn't cross, it visits every vertex exactly once. And that minimizes a trip that someone would have to make. It's related to this, but not exactly that. Yeah.
This one's kind of a little complicated, but if you have a set of warehouses and a set of addresses that they have to ship something to, and every warehouse doesn't necessarily have the item that it needs to ship to that address, you might have to find like the cheapest way to ship something to every address.
Okay, yeah, you're right, that's complicated.
Yeah.
Yeah,
Cheapest way to build train tracks between cities. That
Sure, if you
so
gotta-
all of them are connected.
got to hook a bunch of cities up together with tracks, and you just need a way to get from, make sure you get from any city to any other city while minimizing track. I mean, we're just sort of going off the top of our head here. I think that it's easier to come up with use cases for the shortest task tree. But hopefully that helps. Okay? Okay, so that's Prim's algorithm. Okay, so we want to talk about, get an idea for why it works. And like I said, you can either prove that the greedy choice that's made by those two algorithms is correct, or you can start looking for counterexamples. But if you really want to nail it down after you've thrown counterexamples at it for a while and haven't found one, if you're going to write a book anyway, you got to come up with a real proof. So we got a 2-for-1 here, because this cut property, if we can prove the cut property, then we can use it to in turn prove both those algorithms are correct. So here's the cut property. It says, suppose you got a set of edges. So we've got some set of edges that is guaranteed to be part of a minimum spanning tree. So it could be the empty set. The empty set's guaranteed to be a subset of the minimum spanning tree. It could be an entire minimum spanning tree, or it could be just some of the edges. So that's what X is. And it'll be easier to understand this when we actually look at a graph. But pick any subset of vertices for which, so you pick a set of vertices S with the property that there can't be any edges that start in S and end up not in S. So the division into S and not S is called the cut. There can be no edges across the cut. So if you can do that, then the lightest edge that does cross the cut, so that edge E that crosses the cut will not be part of the set X, but the largest edge that does cross the cut, you can safely pick that edge, add it to X, and still have part of the minimum spanning tree. So rather than try to improve on the words there, just look at the picture right here. Okay? Remember, X is a set of edges, so let's pick the edge AC and the edge EF, just for the heck of it. So I've put them in yellow. So the first question is, are those two edges part of a minimum spanning tree?
Yes.
Yeah, that's part of the minimum spanning tree we've seen like half a dozen times now. Okay? So now we want to pick some vertices, a set S of vertices. And we want the set to be such that there will not be a yellow edge that goes from a vertex in S to a vertex not in S. So what would be a bad set S to pick? Well, B and D would be okay.
DF.
B and D is okay because there are no edges leaving S and ending up not in S. You suggested DF. Okay, DF would not be good, because there is an edge that leaves F and goes to E, which is not in the set. So there are lots of ways to do it. I'm just going to say, let's let S be A, B, C, D. We'll color them purple. And so what's left over is EF. So if we have an edge from a purple to a green, that would be a bad cut. This is an okay cut. So what the cut property guarantees is that the lightest edge that goes from a purple to a green, you can add that to X and still have a subset of a minimum spanning tree. It's safe to pick an edge that crosses a cut. So we would pick this one and add that to our, this guarantees that if we add CF to this set, we still have part of a minimum spanning tree. Yeah?
Why can't we add DF? That also goes from purple to green.
We take the lightest such edge. We want the lightest, here's the cut. We take the lightest edge that crosses the cut. Okay? So that's the cut property. There are two things we could do with it. We could prove it's correct. We could use it to prove that Kruskal's algorithm is correct and Prim's algorithm is correct. Yeah?
So after we added CF, then only B and D would be in S? right?
Well, then we can,
We can do it again.
yeah, you could, okay, so now you've got CF. Now you need to come up with a new set to justify adding the next thing. So the next thing we might do is put A, C, F, and E, make them purple. Make D and B not purple. And then take the lightest edge across that cut, which would be this one here. As long as you can find a way to partition things, then you can pick the lightest edge across and it's safe. So what we're going to do is see that each choice that Prims and Kruskals makes are justified by the cut property. Okay. So here's the sketch. We start with an empty set of edges, x is 0. Okay. So initially, we're going to say x is empty. So clearly, that's part of a minimum spanning tree, right? Then we're going to partition the vertices, and we're going to take the lightest edge that crosses the cut, and we're going to add that to x0, that gives us x1. So now we've got one edge that's guaranteed to be part of a minimum spanning tree. Then we're going to repartition the vertices, add the lightest edge across the cut, and that's x2. And we keep doing that until we get to the end. So it's an inductive, this is sort of the inductive part of the proof. I'm not going to go any further into any formal mathematical induction, but it just shows you can start with an empty edge, justify adding the next edge, justify adding the next edge, justifying the next edge, all the way to the bottom, where each justification is via the cut property.
So is optimal substructure?
Yeah, it has the optimal, yeah, this is related to having, the problem has the optimal substructure problem. Which basically means if your problem has the optimal substructure property, then you can, if you can identify one thing that's part of an optimal solution, then you can reduce the original problem to a simpler one, solve that, add the first choice into that, and have an overall solution. Okay, so let's see. So remember, we're going to start with an empty set, and we want to justify Kruskal's algorithm using the cut property. Well, what's the first edge that Kruskal's algorithm would pick? We must be experts at this graph by now. Picks that lightest edge in the graph. How can we justify that edge using the cut property? Yeah?
A equals S, and then everything else equals B minus S.
Okay. So we could put A in one set, everything else in the other set. The lightest edge across the cut is that one. So the cut property says that is guaranteed to be part of the minimum spanning tree. Okay? The next edge that Kruskal wants to add is that. Okay, how do we justify adding it?
Is E equal E and everything else is?
Yeah, we can take E as one set, everything else is the other set. That's the lightest edge across the cut. Okay? Next one it wants to add is that. How can we justify it?
AC plus S.
Okay? We can take AC as one, everything else is the other. Do that. Okay? And we just repeat. So for that one, we can take A, C, D, F, E, all as one set. B is the other. Take the lightest edge across. That's good. Now we've got, this is one set, that's the other. And we're done. So you play with this a bit and you get to realize that you could always, given how Kruskal picks edges, you can always contrive to find a way for that edge to be the lightest one across the cut. Yeah?
If you have two nodes connected by a yellow edge, do they have to be in the same set?
Yes, if there are two vertices connected by a yellow edge, they have to be in the same, either both in S or both not in S.
Until everything's in one set.
Yeah, and then once everything's in the same set, you're done. Yeah?
I had a question, previous semester, if you have a graph of three, instead of, you have 2 rows of 3, if you have 3 rows of 3, imagine a third row at the bottom, can you do a circle cut of D in the middle?
Yeah, it doesn't have to be that cut doesn't mean you draw a single line. Cut just means you divide the set, the vertices into 2 sets, 2 disjoint sets. So you could have, like, this being part of S, and this thing up here being part of S, for example, and then the stuff in the middle being not part of S. Yeah, it doesn't have to be contiguous. It's just your subsetting vertices. Now, what if we get to a situation where Kruskal's algorithm wants to add an edge between, okay, so A, C, and B are constrained to be in the same set. They have to be both in S or both not in S. What if the edge that Kruskal wants to add isn't going across the cut? What if it's going from A to B, for example? We'd be hard pressed to justify adding A, B using the cut property, right? Because there's no way to put A and B in different sets. So, yeah?
Kruskal doesn't pick edges that would make a cycle.
Right. That's the key. Kruskal wouldn't try that. It doesn't create cycles. So the edges, we can always contrive for the edge to go from S to not S. Okay? Yeah?
What happens if your graph is not connected? Like,
We're assuming, he asked what happens if the graph is not connected, and we're just assuming at the outset that the graphs are connected. They're undirected, connected. Because you can't find a spanning tree if the graph is not connected. All right? What about Prim's algorithm? How do we use the cut property here? It's even easier to see here. Okay? We start somewhere. How do we partition the vertices? So it wants to add that green edge. How do we partition the vertices? What's the recipe?
Everything else.
Yeah, you take yellow vertices are S, everything else is not in S. And at every step, Prim's adds the lightest edge from a yellow vertex to a non-yellow vertex. So by that, it's just by definition, it's following the cut property. So that's the lightest edge from yellow to non-yellow. It gets added. That's the lightest edge from yellow to non-yellow, so it's crossing the cut. So at each step, we're guaranteed to maintain the property that the yellow vertices, the yellow edges are part of a minimum spanning tree. There's the minimum across the cut. There's the minimum one across the cut. Okay? Right, so that's using the cut property to prove those two things are correct. Now, let's prove the cut property. So, we could prove it that way, but I think it's easier to prove it this way. So here's the idea. Suppose that you've got some graph, and I haven't shown, this doesn't show all the edges or all the vertices. The red lines are meant to be edges that that are part of a minimum spanning tree. So imagine we're in the middle of growing a minimum spanning tree. The red edges are the minimum spanning, are part of the edge. Red edges are part of the minimum spanning tree. These two clouds represent a cut of the graph. It's a legal cut because there are no red edges crossing it. And this yellow one is, let's say that's the lightest edge that crosses the cut. So what will the cut property say? Yeah?
the yellow line has to be part of the minimum
Yeah.
spanning tree.
The cut property would say that that this yellow line, if we add the yellow edge in with the red edges, we've still got part of the minimum spanning tree. Okay? Now, how can we approach this? How can we prove it? Yeah?
Proof by contradiction, so we say that.
Okay, he said proof by contradiction. So basically, let's assume there's a minimum spanning tree that does not contain the greedy choice. Now those words should sound familiar. Because I told you last time that many proofs of the correctness of a greedy choice, you assume that there's a solution, an optimal solution that does not contain the greedy choice, and you show that you can transform that into one that does contain the greedy choice. That's how you show that the greedy choice can always be part of an optimal solution. So let's assume that there is a solution in red right there that does not contain the greedy choice. That's possible. We want to show that, nevertheless, there is another solution that does contain the greedy choice, which means the greedy choice was safe all along because it is part of a minimum spanning tree. How would you argue that? How would you argue that there's another minimum spanning tree, same weight, of course, since it's minimum, that does contain that edge from U to B? We'll let them think about it for a minute. Okay, you have to explain. The proof is going to hinge on the fact that this is the lightest edge across the cut. Okay? If you're not thinking about that, you're not going to find the proof. Okay, go ahead.
Was that the only lattice that you crossed the cut? Or?
Not necessarily. There may be other edges of equal weight, but there's none smaller. Okay? Yeah?
Can you demonstrate you can exchange this cut from U to V with some other cut between the two graphs and say that they're equivalent that way?
Well, yeah, we're going to basically take one of the red edges out and replace it with the yellow edge. Okay? So what would happen if we added that yellow edge in? What if we colored it red right now? What would we have? We wouldn't have a tree anymore because we'd have a cycle. Well, for there to be a cycle involving U and V, it's got to get over that cut somehow to get, it starts here, the path is going to end up back at U, it's got to cross the cut somewhere else. And you can see in this example, it crosses right there. So, take it out. And my animation doesn't color that edge red. But the idea is, you find the cycle that goes from U, that involves U and V. You remove the red edge that crosses the cut in that cycle and replace it with UV. Okay? So let's think about that. We take this edge out and replace it with UV. Do we still have a tree? Yeah, it's a different tree, but it's still going to be connected. We just broke a cycle. Can the resulting tree be any larger, any heavier than the previous tree? How do you know? Because this is guaranteed to be the lightest edge that crosses the cut. So if that previous tree was a minimum spanning tree, that just says that that red edge that we took out has the same weight as that yellow edge. So we start with the red tree and we turn it into this tree. Color that red in your mind. That's also an equally light spanning tree.
What about that line further up that doesn't create a cycle?
Well, the line further up that doesn't create a cycle, what about it? So the red one at the top
Yeah.
crosses it's not, is there no consequence? I mean, it can't be any lighter than this one. But why do we get rid of the one in the middle instead of the one at the top?
Because that's the one that created the cycle.
Right, because that was one involving the cycle. We got to remove the one that crosses it as part of the cycle. It's possible there could be multiple choices to eliminate, because it could meander back and forth across before it gets back to you. We just got to get rid of one red edge that crosses the cycle and replace it with that yellow one. And we're good.
We claim that the edge from U to V is the lightest one between the two sets.
Yeah, that's what the cut part. You can't apply the cut part unless you're talking about the lightest edge across. So what we've got now is a justification for why it's always safe to pick the lightest edge across, because it's guaranteed. You combine it with the existing set X, it's guaranteed to be a subset of a minimum spanning tree. Okay. And this here, what I skipped over, is just the same thing in words, basically. It's a lot easier to look at the picture. So there's the subset, there's the whole one. That's still a minimum spanning tree. Okay, so there's Dijkstra's algorithm, we've seen before. Here's Prim's algorithm. So the differences are in yellow. And you can see, the only thing we have right now, that we didn't have before, is that in-tree array. So we have to keep track, basically, of the yellow vertices. And we do that with in-tree. And here, we've got to make sure we're not looking at an edge that goes from a yellow vertex to a yellow vertex. And I guess I should have highlighted this difference here, too. Okay. Yeah, and I called one array distance and one array cost. Anyway, there are more differences than are highlighted in yellow, but the major differences are highlighted in yellow. It's a very similar algorithm. Here, the distance is calculated that way, cost is calculated that way. That's the heart of the difference. So what would you expect the complexity of Prim's algorithm to be? going to be the same as Dijkstra's. Same data structures into the same structure.
So E log V.
So if it's adjacency list, it would be E plus V log V. Okay, but then there's Kruskal's algorithm. Now what is the challenge in implementing Kruskal's algorithm? Yeah?
It's implementing disjoint sets, which you can.
Well, but why disjoint sets? What problem do you need to solve to come up with an algorithm for Kruskal's algorithm? What is the greedy choice? Yeah?
Adding edges that don't create a cycle?
Right. We have to be able to identify an edge that causes a cycle or one that doesn't cause a cycle. We've got to be able to tell the difference efficiently. Now, we know how to tell if an edge is part of a cycle. I think that was on assignment. But it involved the depth first search. We can't afford to do a depth first search every time we're deciding whether to add an edge or not. So, we're going to invent a new data structure called the disjoint set data structure to solve our problem. So, push Kruskal's algorithm on the back burner now and look at this, and then we'll see how it's used. So these are the operations for a disjoint set data structure. We can create a disjoint data set, and n is the number of elements there are. So what n does is it creates a collection of n sets, each set of size 1, each one contains an integer 1 through n. Okay? So those are, if n is 8, you're going to get 8 sets. The first one contains 1, the second one contains 2, and so on. There's a find operation that returns an integer that uniquely identifies a set to which it belongs. Now, for the next few slides, we'll always have find return the largest element in the set. But we'll change that eventually. You just got to be able to uniquely identify it. And then union just combines the two sets to which x and y belong. So let's look at this in action. If we call the constructor, that's what we get. We get a collection of 8 sets. D.find, if we do find of 3, for the next slide or two, we're basically asking what's the largest element to which, in the set to which 3 belongs. Well, this is the set to which 3 belongs. The largest element is 3. It's the only element. Similarly, if we do a find on 5, the largest element is 5. Largest isn't important. We could be smallest. We could do something else. As long as every time you ask, you get the same answer. Okay? Then union. This says, take the set to which 2 belongs and the set to which 7 belongs and put them together. And this says, take the set that 5 belongs to and the set that 8 belongs to and compute their union. How would that change this up here? What's going to happen when we take the union of 2 and 7? Yeah?
2's value becomes 7.
Well, what happens to the list of sets? Yeah?
Gets reduced, 2 and 7.
Okay, so 2 and 7 get smushed together into one set. And the sets for 5 and 8 get smushed together. So you get this picture here. So now you've gone from 6 sets to 8. So the way this data structure evolves over time, as you do unions, you gradually get fewer sets until everything's in one set. Okay? So now we do a find on 3. Let's see. Largest element in that set is 3. We do a find on 5, it's going to return 8. Because that's the largest element in that set. We do a find on 8, we get 8. What if we do a find on 2? You get 7. Okay? Now we take the union of 1 and 7.
So you merge those two sets.
We merge these two sets, we get 1, 2, 7, and then we do the 3 and 4, that puts them together. And, oh wow. Strung a lot together there. But 1 and 7, put these together, 1, 2, 7. 3 and 4, put these together. So you get that, and then we take the union of 4 and 6. That takes the 3 and 4 set and the 6 set and glues them together. So now we only got 3 sets. If we do a find of 3, we get back 6. We do a find of 5, we get back 8. A find of 4, we get back 6. We do this union and that union, and now everything's in one set. So maybe you don't see what this has to do with finding minimum spanning trees, and that's okay. I want to make sure that you got an idea of what the data structure does. So let me pause here and see if there are any questions. So just those 3 operations. Yeah?
runtime complexities for find, is that n by chance?
Okay, he's asking about the runtime complexity for the find operation. And that's a good question. The way we've talked about it here, this is a very inefficient implementation of the union find data structure, of the discrete set, disjoint set data structure. I will stipulate for now that we can do it in log n time. Find operation can be done in log n time, or n's the number of elements. You know, n is a parameter of the constructor. We can actually do better than that. But for now, let's just assume it takes logarithmic time for both union and find. Yeah?
One more question. Would this be back in a adjacency list?
Say again?
Would this be stored in an adjacency list?
No, this has nothing to do with a graph representation. This would just be off to the side. Any other questions? All right, well, let's see how we can use this data structure to implement Kruskal's algorithm. So let's see what we do. We create a new disjoint set data structure using the number of vertices as a parameter. And so we're going to end up, the way to think about it is, you're going to end up with these sets. What will each set contain?
Singletons.
Each set will be a singleton set containing
Just the
a vertex name, vertex number. So if your vertices are A through X, you'll end up with 24 sets, each one containing one vertex name. Okay? Then you sort the edges by weight. So you take the edges, sort them by weight. Okay? Ascending order of weight. And then our set X is, we're going to build our spanning tree using X. So we start out empty. So then, what we do is we just iterate through all the edges by increasing weight. So we're going to look at each edge one at a time. And then we ask, does ds.find not equal of u not equal ds.find to v? Okay? So what's going on here? How are we using a union find data structure? What does it represent at any point? Yeah.
Are you saying if u and v are equal on the same set?
Okay, right. So this is saying we're going to use an edge if, let's say you got an edge uv, we're going to add it to the minimum spanning tree as long as u and v, the two endpoints, are in different sets at the moment. So what are we using the sets for? Yeah?
Set membership. Two objects are in the same set, there's an edge that connects them.
Okay, if two vertices are in the same set, there is a path that connects them. Okay? So if, as you add edges, the vertices are connected. There are going to be different connected chunks in the graph. So that data structure, the disjoint set data structure, represents the clumps. So initially, every vertex is its own clump. If you add an edge from A to B, then you take A's clump and B's clump and put them together. Now you got a bigger clump. What's going to be the case at the end of this? Is if every time we add an edge, we combine the clumps of the two endpoints. Yeah?
It's all one clump.
We're going to end up with one clump, because at the end, they'll all be connected. And that means there's one clump. So what we do is, if we look at the edges in increasing order of weight, because we want to get the lightest edge, if ds.find of u is not equal to ds.find of v, that means that u and v are currently in different clumps, and it's safe to add the edge. So we add the edge, and then we combine the u and v clumps into a bigger clump. Yeah?
So shouldn't we have an early exit that once we find that we have everything's in one big clump, then we can exit the...
Yeah, we could exit. I mean, it may be that maybe you get lucky and there's a whole bunch of edges, but the first v minus 1 get added. And the rest are a waste of time. So yeah, you could break this loop as soon as there's only one set in the disjoint set data structure, or when you've added v minus 1 edges to x, or any number of things. Okay, so the thing you should picture is the disjoint set data structure is representing the connected clumps that are defined by the edges that we've added so far. Initially, everything is its own clump. At the end, there's only one clump. In the middle, any edge you add has to go from one clump to a different clump. When you add that edge, you smash the clumps together. Now, why are we inventing a new data structure? Why not just use a hash set. Why do we do this? Yeah?
It must be more efficient somehow.
Yeah, it turns out to be more efficient because we're using these sets in a very a different way than you use regular sets. We're not interested. We never look something up and say, is this in a set? We're just asking, are these in different sets? And when we combine, we could, if we represented, if we used just regular sets for this purpose, it would just be a lot less efficient. So we're sort of creating a custom representation. All right, let's analyze the complexity. So look at that and tell me, what's the cost of Kruskal's algorithm? Yeah?
It's E times the cost.
Well, let's take it step by step.
So
What's the cost of that first operation?
cost V times some constant.
Yeah, so creating the data structure in the first place, it's got to create V little sets. So it's going to be O of V. Okay? What about the sorting the E edges by weight? Well, you got to get the edges first. That's going to take whatever the cost of enumerating the edges is. That depends on the representation. Plus, then the cost of sorting will be, let's say we do it with merge sort. It will be E log V. Okay? Let's see what I got here. So O of nu is the cost of creating the disjoint set data structure. We argue that's O of V. We have to enumerate the edges. We have to sort them. Okay? What else do we have to do?
Then for each edge.
What do we do for each edge? Yeah. This edge will run, this thing runs once for each edge. What do we have to do? How many times do we do a find operation? Twice per edge, right? So in big O terms, that's just E times the cost of doing a find. And what's the, how many times do we do a union operation?
One per edge.
We do one per edge, or one per vertex rather.
Yeah.
And that's the cost. Now we're going to assume that we're using adjacency lists, just to simplify things. And we're going to assume that the graph is connected, so we can simplify it. Okay, where did those simplifications come from? Okay, O of nu became O of V. We already said that. Cost of enumerating a list is V plus E. Cost of sorting is whatever sorting algorithm we use. E find V times union. That's not much of a simplification. So, we throw out the O of V and the O of V plus E because there's E's and V's down here and they're worse. So it's the cost of sorting, E times the cost of find, V times the cost of union. So let me just do this all out here. So Prim's algorithm, we said, okay, it's Dijkstra's algorithm in terms of complexity. Kruskal's algorithm, that's what we just came up with. We can certainly do the sort in time E log E. And I'll just tell you, you can do the find and the union each in logarithmic time. So under that assumption, you get, this is the cost of all the union finds. Since the graph is connected, you know that E is bigger than V. Since E is at most V squared, log of E and log of V and log of E are the same complexity. Log of E is at most 2 times the log of V. Anyway, the bottom line is it simplifies to this. O of E times log of V. Well, Prim says, yep, O of E times log of V. But
V squared for X graphs.
yeah, I didn't analyze Kruskal's for the dense graph. We can do better. Okay, so this is, I kept promising you we talk about rated sort. So we can improve the bottom line on Kruskal's algorithm by coming up with a faster sort and coming up with a faster union find operations. All right, so we'll take a break and then we'll see how to do that. Okay. So we got two things to talk about now. One is, how do you implement disjoint sets? And the other is, how do you do sorting in linear time? Now, neither of these topics has anything to do with greedy algorithms. It's just topics that come up because we've been talking about here. They're sort of necessary to speed up Kruskal's algorithm. So let's look at disjoint sets first. All right, we already saw this slide. That was the example of how a disjoint set works. And we saw that slide too. That's the last slide we looked at. And this is the cost. So we're going to lower this cost by looking at radix sort. We're going to lower these costs by looking at how to implement the union find beta structure. Okay. So here's the deal. Let's say we want to create a new disjoint set. What we're going to create is 8 trees. Okay? And there we have it. So we're going to represent our sets. Each set's going to be represented as a tree. It's going to be different than trees you're used to. One difference is it's not a binary tree. It could be any number of children of a vertex, of a parent. Okay? In this case, the tree consists of a single root vertex for each set. A single node. And then we're going to annotate the root of the tree by its depth. Right? So all these trees have depth 0. All right, to do a find operation, somehow you've got to find the tree that A belongs to. And then you've got to travel to the root of that tree. And rather than report the largest element in the tree, we're going to report the element at the root. So we'll see later how to find the tree that A belongs to. But in this case, to do a find of A, we just go, we go to the tree that contains A, travel to its root. Well, we're at the root. And we report A as the answer. So we're not reporting the largest anymore. We're reporting the thing at the root. It just has to be consistent. Then we do a find on F, same thing. We go to F, we travel to its root, we report F. Okay? To take the union of two things, what you do is you just have the root of one point to the root of the other. So we do a find on A, we find the root of A's tree, we find the root of B's tree, and then we have B point to A, the root to the root. And why did the superscript on A go up? The depth went up. Okay? So now we're down to 7 trees. And you're starting to see some structure. So here's the other odd thing about these trees. The children point to the parents. You're probably used to thinking it the other way. But here, we're only interested in, we just travel up. Okay? Now we do a union of B and C. Okay? So what are the steps to do a union? Okay? We find the root of the tree to which B belongs. So we go to B, go to its root. We go to C, go to its root. We've done that. And then we have the root of one point to the root of the other. Now, I think we want to keep these trees as shallow as possible. Why do you think it's a good idea to keep these trees shallow? Keep the depth down. Right, the find operation has to travel to the root. So the shallower these trees are, the less work find has to do. So should we have C point to A, or should we have A point to C?
C point to A.
Right, C should point to A, because if we do that, we don't have to change, the depth of A doesn't change at all. What if we'd done the other way? What if we had A point to C?
C's depth.
C's depth would be 2. So how can you tell which way you want to point? Yeah.
Just compare the depth of each.
Right. You compare the depth. You want to have the lesser depth point to the higher depth. And if you do that, if you have one depth that's lower and the other that's higher, and you add that arrow, the depth doesn't have to change. When does the depth go up on one of these things? Right. When you have, like the case where we had A was 0 and B was 0. So you have 2 trees of equal depth. If one points to the other, the depth of the new root has to go up by 1. So we want to avoid that if we can. Okay, let's do a find on C. What would that look like? You go to C somehow. We haven't talked about how to find C. You can imagine there being an array that points up to each of those things. So you find C, you travel to its root, and report A as the answer. So find on C would be A. Let's take a union of E and D. What would happen? Equal weights, equal depths rather.
E points to D.
So E points to D or D points to E, either way. So there's E, there's D. I'll have D point to E. And we'll give it a, now that the depth goes up because they were equal depths. Okay, union of F and G. There's F, there's G. Just like that. Let's take the union of D and G. You go to D, go to its root. Go to G, go to its root. Equal weight. So one points to the other and the depth goes up. Okay, do a find on G. You go to G, to F, to E. Report E as the answer. So you can see these, it's the find operations that are expensive. Because potentially they start at the, on a leaf and go all the way to the root. What about the cost of a union operation?
It's cost of a find.
Well, the union has to do 2 finds. But then once it's done the finds, the rest is cost of time. So really, both union and find have the same complexity because it's the complexity of a find operation. You have a question?
Say we do a find on G, and we find that its root is E.
Yep.
Should we have G just point to E now?
Ah, interesting question. He said, as we do a find on G and we find out its root is on E, why don't we, as part of this, just restructure the tree? We know that G's root is E. Let's just put a shortcut. Take that edge from G to F out, put the edge directly from G to E. What do you think of that?
How costly is it?
What will, that's,
Constant.
it's constant. You're just flipping a couple references.
But if it was a deep tree,
Well, you're doing the work anyway, right? You're starting somewhere, you're going to the root. You now know the root, you know the start. You can just stick in a shortcut. Does that screw anything up? Yeah?
Doesn't that make it so that E has 3 children?
Sure. E can have 3 children. E can have any number of children.
Yeah, but you couldn't have a login like running out of search. You'd have more than 2 choices to make.
No. It doesn't matter how many branches are in the tree because we're only ever going from a vertex to the root via a straight line. There's no branching you consider. Yeah?
Would you have to fix the levels because F is E?
Okay. The one price you pay, if we put a shortcut in from G to E, then suddenly, technically, the depth of E is no longer 2 but 1, and the depth of F is no longer 1 but 0. So let me just, long story short, what he just proposed is in fact an optimization that we're going to do probably next time. Okay? That's what makes this even faster. And when we do that optimization, the depths, instead of being actual depths, they become sort of upper bounds of the depth. It's too expensive to fix them up. So we'll use that idea. Yeah?
Why do we care about the depths?
Why do we care about the depths? Okay? Who can answer that question? Why are we keeping track of the depths? Yeah?
When you do your find operation, if it's at the bottom of your tree, you have to travel all the way up to find the root.
Okay. So
why not just check if there's no parent? Like, why do you need to know how high up you need to go?
when we do a union, we want to do the union in such a way that the depth is minimized. Ideally, the ideal shape of one of these trees is one root that everything points directly to. So just 2 levels in the tree. We want to keep the tree as shallow as possible, and to do that we need to know the depths, so we can have the lesser depth point to the higher depth. Big depths are bad. Okay? What happens when you take the union of H and D? There's H, we found its root. Find the root of D, we go there. Now what will the pointing look like? H will point to E because E has a higher depth. We want to keep it at 2, not make it go up to 3. Pointing the other way, H would become a depth of 3. Okay? We do a union of C and H. So we go to C, find its root. We go to H, find its root. A is depth 1, E is depth 2, so the pointer goes from A to E. Okay, so it's a weird looking tree. E has 4 children. But we never go, you can't go from a parent back down to a child. The pointers don't go that way. Okay? Now, it turns out that this thing I'm calling depth is also called rank. The maximum the rank can get is log n. I'm going to show you why now. But why is that important to know? What does it tell you? If I tell you that the depth of the tree, the depth of the deepest node can never be bigger than log n. What does that tell you? Yeah.
That's the cost of the find operation.
That's the cost of a find operation and also the union operation. We can see that the depth is never more than log n. Then that puts a bound on the cost of the operation. That's before we add your optimization. If we add your optimization, we make it even better. So let's see why that is. So here's the challenge. I want you to take these 8 nodes and build the deepest tree you can. You can do the unions in any order. You get to pick, but your goal is to end up with a single, you do 7 unions, you end up with a single tree. I want you to make it as deep as possible. So if we were to contrive to make it as deep as possible, what's the worst we could do? Yeah?
The only way you increase levels is by matching the same level.
Exactly. The only way the level increases is by matching same level trees. So if we want to have a tree of depth 3, what do we have to make first? 2 trees of depth 2. If we want a tree of depth 2, what do we have to have?
4 trees of depth 1.
Yeah, to make 2 trees of depth 2, we need 4 trees of depth 1. And to make 4 trees of depth 1, what do we need? 8 trees of depth 0. All right? So let's just see how that works. Well, first we'll make 4 trees of depth 1. 1, 2, 3, 4. We do those unions. Now that we got 4 of those, we can make 2 trees of depth 2. 1, 2. And now that we got those, we can build a tree of depth 3. So it took 8 little sets to make one of depth 3. So that's 3 is the log of 8. If we wanted one of depth 4, what do we have to do? We'd have to repeat that. We'd have to have 8 more vertices, 8 more elements. We would do this on those. Now we have 2 trees of depth 3. Then we can get one of depth 4. So the depth, the maximum depth is logarithmic in the number of elements you start with. Now, the optimization he proposed, how would that help? Okay?
Every time you do a find on the maximum depth, you reduce that to just 1.
Okay. So you're doing finds. Even if you're just doing union operations, you're doing 2 finds every time. And so his optimization would tend to reduce, it can't make things worse, and it tend to reduce the depth of the trees. It can't hurt, and in fact it makes things a lot better. Or better anyway. Okay, so that's the game we're playing with disjoint set representation. Now, in reality, you don't need to use dynamic memory and pointers to do this. You can just do it with a couple of arrays. So I've got that array called rank, which contains the depths. I sort of start out calling it depth instead of rank, but in your book it's called rank. And down here, we store the parent. Look at the in between the 2 arrays, those are the indexes. So we're indexed by vertex name. So for every vertex, we know its rank, and we know its parent. How do we denote a root? Look at that and tell me how we denote a root. Yeah?
It's a self-loop.
Yeah, so if something is its own parent, that means it's a root. All right, so let's repeat what we just did, but with this representation instead of the one that uses pointers. So we create the new disjoint set, so there you are. Now we do a find on A. So how do you get started with the find operation? How do you find A? Yeah?
Start at wherever you start at A and then go to its parent
Right.
elements itself.
Right, so we got the index there. So we just go to index A and we look in the parent array, and there is that. And we notice that we are at the root because that it's storing its own vertex name. So that's the find operation. Okay, what about find of f? You go to index f, notice that that's its own parent. Okay, what about union of a and b? Yeah,
F.
Find the root of each,
right? You find the root of a,
and then you set one to be the other.
okay? So you got to union those two things. You notice they have the same rank, so one has to refer to the other. So let's suppose B is going to point to A. What's going to change in my picture?
Parent of B becomes A.
Right, so B's parent will change to A, and A's depth will change to 1.
Right.
Right. Okay? Great. Now we take the union of B and C. So we go to index B, we say, no, B's parent is A, so we go there, and we say, oh, we're at the root. C's at the root. We take the union, rank 1 and rank 0, so we want C to point to A, so the entry in C will change to A, and A's rank will stay the same. Rank only goes up when you're unioning things of the same rank. Okay, we do a find on C. We go there, C's not stored there, so we go there. We find A. We do a union of E and D. Now, that's very familiar. There's E, it's its own root, D's its own root. We do the union. D now refers to E as its parent, and E's parent just went up to 1. We do the union of F and G. Okay? Same thing. There's F, there's G, there's the union. We do the union of D and G. We go to D, we go to E, that's the root. We got to find G, so we go to G, we go to F, that's the root. One has to point to the other. So I'm going to have the green one point to the yellow one. So what will be stored at index F of the parent array? E. And what will be stored in the rank for E? 2. Okay? We do a find of G. We go there. That's not the root. So we go to F. That's not the root. We go to E. That is the root. So it's just, again, that find is just governed by the maximum depth of the tree. We take the union of H and D. Let's see. H is its own root. D is not the root, but E is. So what will point to what? H will point to E. So H will, the entry, that yellow thing will become an E, and the rank of E does not increase. And we take the union of C and H. So C, A, that's the root of C's tree. H, E, that's the root of E's tree. So we want to have A point to E, because A has the less rank. So that yellow thing will become an E, and nothing else changes. And what else? Yeah.
So rank only half of the rank array ever gets filled, or can even get filled.
Right, there'll be a lot of zeros left.
So is there a way to use less memory?
We could use, I mean, the best we could do is say half of the memory, but that's just a constant.
You kind of have to know in advance too, which ones
Yeah.
you're going to use.
Well, you could use maybe a hash table instead of an array. I can't imagine that being worth it. Okay, so here it is in code. So we just did the simulation. You got the parent array, the rank array. This guy here just fills in the numbers. Everything's a self loop, all the ranks are 0. Find just iterates until x is equal to parent of x and returns x. So it's just following the numbers, so that's efficient. Union just does the 2 finds, and then what it does, if the 2, what's that mean? If r of x and r of y are the same, how's that going to happen? If x and y are already part of the same tree, there's nothing to do. Otherwise, what you do depends on how the ranks compare. Only in this case, where the ranks are the same, you actually increment the rank anywhere. Okay? So now we know that this is linear time, this is logarithmic time, that's logarithmic time. And there's a picture that sort of shows both data structures. This is the first one we played with the explicit pointers. That's how you could actually do it. It encodes the same information. And that's the complexity there. A lot in throughout. Okay, so before we look at the next slide, are there any, sort of went through here, see what questions I have. Yeah.
Just curious, with the array implementation, how does it know when to stop?
Okay, so he asked, when we're doing this search here, okay, it stops when it finds, let's go forward here. Let's say it's doing a find on G. So G stores an F, they're different, so we go to index F, that stores an E, they're different, so it goes to index E, it stores an E, they're the same. So when it finds that little self-reference, that's when it knows it's at the root. Yeah?
Maybe you already answered this, but why wouldn't you want it so that one node is the parent of all the others?
You would.
You only have one level.
Oh, you would love that. You would love it so that one node was the parent of all the others.
Right.
But it's too much work to get it in that form.
Okay.
And so it's too expensive to always keep it in that form.
Okay.
The next best thing is to, whenever possible, when you're already doing a find, flatten the tree a little bit as you do it.
Okay.
And so you sort of approach that. You don't quite reach that ideal, but you get pretty close to it. What other questions? There's the complexity. There is, so that's Kruskal's algorithm. So now, this was our thing originally. And at this point, E log V is smaller than E log E, or no bigger, because the trees are connected. The graphs are connected. And V log V for the same reason, since it's connected. So that's our dominant term right there, E log E. And really, what is E log E? Where did that come from? That's the sort. So if we want to make any progress on this, we need to come up with a faster sort. Now, in preparation for the faster sort, which obviously we'll talk about next time, let me tell you a sorting problem that I face. So I give about 4 exams a year, a semester. And so that is 8 per academic year, and I've been teaching for 31 years. So that's almost 250, is that right? 8 times 31? 250 exams I've given and graded. And every time we got to sort the exams at the end. So I've got a class of, last semester I had a class of over 300. What's a fast way to sort exams? Do we use quick sort? Do we use merge sort? Do we use heap sort? Insertion sort? Yeah?
So you look at the first letter of everyone's name and then you put them in a separate pile
Right.
and then...
What we use is called bubbles. It's not bubbles. It's bucket sort. Bucket sort. So essentially, we go into a room with a long table. Me and all the TAs each take a piece of the stack.
Multiple long tables.
Yeah. And we basically just conceptually say, okay, all last names that begin with an A go here, B's, C's, D's, and so on. And we just sort of, in parallel, we're like, okay, Anderson goes here, and Wu goes here, and Smith goes there, and we're sort of dodging each other. Very quickly, we've got our piles into buckets. And that takes linear time, basically. Actually, better linear time because we do it parallel. Then what do? We got the buckets. Yeah, the buckets are now small enough, typically. Now, when you get to 300, it's starting to push it, because it's always the S's that are the problem. And so I've learned to avoid the S's. In parallel, again, we just sort the buckets. Probably insertion sort is what we're doing there. We're just grabbing a pile and sort of rearranging them. And we've gotten it down to the science. We're so good at it now that I don't have to participate anymore. So
You always find something that you got to do.
Right. I gotta go to my exercise. Let me just give, the final thought is, we're going to study rating sort next time, among other things. Counting sort is bucket sort. Also counting, anyway, bucket sort is sort of the basis of rating sort.